Hello and welcome to EP2P04 topic number 8, Flexural Elasticity. This is the third elasticity topic we're going to deal with, and it is the response of a beam to bending moments, which are moments about the ends of the beam that cause the beam to go from this kind of a shape to this kind of a shape. Bending is usually the dominant deformation method in most beams because most beams are pretty long in one dimension compared to the other two dimensions, and being long in that one dimension makes two things happen that emphasize how much bending deformation will be important. So for one thing, it means that any forces that are applied along the beam perpendicular to it, like any shear forces on this beam, maybe at one end or the other end, are going to be producing higher torques on this beam. They're going to need to be responded to with higher internal bending moments. So being long in one dimension compared to the other two means that you have higher internal bending moments needed to respond to those forces perpendicular to the length direction. But it also means that the internal bending moments are resisted less. So the ability to resist bending is lowered if the beam is really thin in the perpendicular two directions compared to its length. Imagine how difficult it is to bend a really thin thing in the thickness direction versus bending something that's a lot thicker. So imagine you've got a thick board of wood and you're going to compare how hard it is to roll that up compared to a piece of paper. Well, the biggest thing that makes a piece of paper a lot easier to roll than a board of wood is the fact that the paper is much, much thinner. Let's quantify this stuff a little bit. So if you apply pure bending moments to a beam, which are the moments that are going to cause it to bend, so not a moment that is in the same direction as the length, but a moment that is perpendicular to the direction of the length, either out of the page or up and down, which would cause it to bend out of the page. The moment that's along the length direction will lead to twisting. We'll deal with that next week. But for now, this kind of bending moment, or one that is directed up and makes it bend out of the page, will lead to a curvature of the beam. So other things equal, pure bending will tend to bend it from a straight beam into an arc of a circle where the circle has a radius rho, and the bigger the radius, the less bending has happened, right? Like a straight beam can be thought of as bent into the arc of a circle that has infinite radius, so the smaller the radius, the tighter the circle, and the more bending that's happened. So usually it's better to talk about the curvature, which is the inverse of the radius of curvature. And this way, you can say that this beam has no curvature, and now we've got more curvature, right? We've bent it, and it's increased the curvature. If you want to relate that to a physical quantity, then you can take the inverse of the curvature, and that is the radius of the circle that we have bent the arc into. Okay, so in pure bending, a bending moment causes a curvature C according to the bending Hooke's law, right? The elasticity relation for bending, which is that the bending moment is related to the curvature by this material and geometry parameter, the flexural rigidity, EI. So in this formula, E is the stiffness of the beam in the length direction, the Young's modulus in the length direction, really the effective stiffness. So if you're clamping it in the Z direction, for example, then you would use the effective stiffness in the length direction in this formula. But if it's free in the other dimensions, then that ends up just being the Young's modulus. And I is the second moment of area of the cross-section about its centroid. But specifically, it's not just the regular centroid. It is the stiffness-weighted centroid. Again, if the stiffness could be different at one part than another, then you would use this kind of weighted average where you don't just take the average y, that would be like the location of the regular centroid. You weight both the integrals and the average by the stiffness. So the stiffness will cancel if it's uniform across the cross-section, and you'd end up with just the average y, the non-weighted centroid of the cross-section. Let's talk about averages and weighted averages. In general, the average value of some function of position over some area is the integral of that function over the area divided by the area, which is like integrating the function over the region you're talking about divided by just integrating 1 over that region. So this is the average value of this function f over that region. You might give it a symbol f bar on top to show that you're talking about the average of f. And this is not a function of position because you've gotten rid of the position dependence by doing this averaging, right? So the average y position, for example, would be when the function is just equal to y. That's the function of position, right? It just says whatever the y coordinate is, that's what I'm going to return. It's kind of a simple function, but it still works. You can substitute that into this formula and see, aha, we've just got, that's the y bar. So this is the average position. In 3D, you wouldn't be dividing by the area and integrating with respect to area. You just do the same thing, but the integral is with respect to volume, and you divide by the volume. In 1D, you could find an average by integrating over some length, some range of x maybe, and then dividing by the total length, the just difference between the final x position and the initial x position. So that's one way that you can take an average. These are all technically non-weighted averages. You could also have weighted averages. Weighted averages are the same thing, except in the numerator and denominator, for both of the integrals, you add in some other function, right? So imagine you're going to have a weight function, w at r, and you put that in the numerator and the denominator. Now you are figuring out the w weighted average of value f, and maybe we'll give that a different symbol, maybe capital F, to keep in mind the way we're using things up here. So capital Y bar is the E weighted average Y position. It's going to be the same as small y bar if E does not actually depend on position. Why would you use this? Well, for one, in calculating the stiffness weighted centroid, this is going to be effectively giving more weight, right, more emphasis to the parts of the area where the stiffness is higher. So if you have a combined cross-section, like your cross-section is part steel and part of it is wood, then the steel part, which is much, much stiffer, has a higher Young's modulus, is going to have much more weight on where the average position should be, where the centroid should be, where the center of the bending should be, than the wood part, because the wood being there doesn't really affect the steel that much at all. It's so much less stiff than the steel, so the steel is just going to say, well, the center is still centered on me. I don't care about that wood being there. So that's why you use the stiffness weighted average position to figure out your centroid that we're going to be bending around in calculating flexural rigidity. Another example of where you would use this is with density. You take a weighted average position where the weight is the density function in order to find the location of the center of mass. If you think back to this steel and wood example, steel is also much denser than wood. So the center of mass of a beam that has like half steel and half wood is going to be way in the steel part, and the way you would calculate exactly where is by doing a weighted average by density. All right, a couple of notes on beam bending. Once the beam has started to bend, then its cross-sections that were originally in the YZ plane, these like end cross-sections here, are going to be rotated so that they're actually not quite in the YZ plane anymore. They're rotated about Z for the bending that we're showing here from moments in Z. So they're like less in Y than they were and a little bit in X. They used to be not at all in X. They were just in the YZ plane. So what we do to keep all of this stuff less confusing when we're talking about it is keep X, Y, and Z as the coordinates of any point in the beam before deformation has started. And then after the deformation, if we've got a displacement of U, V, and W in X, Y, and Z as usual, then we'll say that the new point is at X plus U, V, Y plus V, Z plus W, but X, Y, and Z remain the coordinates of that given point before deformation. So you would still say that that this point, this line here, because it was originally in the is it in the YZ plane? It depends. Well, originally this surface was parallel to the YZ plane. This thing, in terms of its Y, Z, and X coordinates in the original reference frame, are all at the same original X value. So we'll keep track of X, Y, and Z as a way to refer to the points before the bending actually took place. So next thing, you'll sometimes see in math or other engineering books on this that the that we have a name for this integral of y over the cross-section. That's called the first moment of area about the z-axis. This is the cross-section's first moment of area about the z-axis. I'm not really going to use this because it's confusing with our moment notation, but just in case you're looking at other sources and you see this thing referred to, or you hear somebody talk about first moment of area about the z-axis, that's what they're talking about, just the numerator in this thing to locate the average y position. All right, next, when we're bending like this, there's an axis somewhere in the middle that doesn't change length. So to do this bending, you notice the top line has gotten shorter, right? And the bottom line has gotten a little bit longer than it was originally. So somewhere in between, there's a line that stays exactly the same length. It has no strain, and in fact, no stress because of that. And that's called the neutral axis. In 3 dimensions, it's the neutral surface or neutral plane through this material. So above, we've got compression. Below that, we've got tension, at least for the bending in the positive z direction like we're talking about here. And right at the neutral surface or neutral axis in 2D, we have no deformation at all. Okay, now where does this come from? We said above that it turns out the moment is equal to the flexural rigidity times the curvature that shows up, where curvature is defined as 1 over the radius of curvature that the beam bends into. Where does that come from? First, what we're going to need to do is figure out how the radius at every point y is related to what that y value is. So let's imagine we've got some coordinate system within the beam, and we're going to call rho the radius at the neutral axis. So wherever the neutral axis is, it doesn't matter. We're going to say that rho is the radius that we've bent into at that point. So if you were to figure out what the radius of curvature of this neutral axis is, that happens to be rho. Okay, so then the radius at some point y, a distance above that, where again y is a local coordinate, so it stays kind of pointing perpendicular to the neutral axis, even though the neutral axis is kind of bending. So the radius at some point y above is decreased by y, right? So it's just rho minus y. If you were to go to a negative y, then the radius is increasing that way, and it's decreasing that way. So that's why the radius at a position y is rho minus y. Okay. The strain in the x direction at some point y is going to be dependent on that y point, right? So at positive y values, we're going to have more negative strain. We've got compression up above the neutral axis, and we've got tension down below the neutral axis. How do we find out what that strain is? Well, we're going to look at how the length of this thing has changed, right? So if the original length is L, that's still the length of the neutral axis, right? So the strain being delta L over L, the change in the length divided by the original length, will be the new length minus the original length over the original length. And the new length is the new radius times the angle that goes through that this whole arc is subtending, right? So this angle, whatever it is, phi, is going to cancel anyway. So just say like whatever, it could be like a small segment of angle locally, or it could be the whole angle of the beam. Doesn't matter if it's in uniform bending. We've got that the new length will be the new radius, rho minus y, whether y is positive or negative, and then that radius times phi, the angle. Whereas the original length is the original radius times phi. So that's still the radius of wherever the neutral axis is. Okay, so cleaning up some stuff, the rho phi cancels, and then all the phi's cancel, and we've got negative y over rho. All right then. So phi again is the angle, is the arc angle of the whole beam once it's bent, and we've used the arc length formula for the neutral axis, that the length of an arc is the radius of the circle that it's an arc of multiplied by the arc angle. So if this thing is the strain, then the stress has to be equal to that times the stiffness in the length direction. And so we're just going to call that E, keeping in mind that we would have to replace the regular Young's modulus with really the effective stiffness in the length direction if we've got some strange boundary conditions going on like we saw earlier, like we saw a couple weeks ago, that is. So using the strain that we just had, this tells us that the stress is E times negative y over rho. All right, so that's the stress that has to be present at that surface for it to be changing length in the way that it is. Next, what we can do is we can figure out, since we know what that stress is, what the total force is on a little segment of it from adjacent faces. So if we have a stress on it of sigma, then that means there's a little bit of a force, dx, at this point compared to the neutral axis. We've sort of said y equals 0 is where the neutral axis is in this coordinate system. And the stress above this is going to lead to a little bit of a force over area dA, which is dF, sigma, and dF is equal to sigma dA. So then, the stress that we got, if we substitute that in, that means that we have a little bit of a force at position y, which is negative E y over rho dA. And we can integrate this to find the total torque on this face produced by those stresses. So the moment that is put on the face from those stresses is equal to the integral of negative y times this little bit of force. Why negative y? Because if you use the right-hand rule, we take a step up and dF to the right by tension being the default for sigma, tells us that we've got a moment into the page. So the net torque produced by this stuff is equal to the integral of negative y times this little differential force. Substituting in what we found that differential force has to be given the length change that shows up in bending, we end up with the negatives canceling, and that the moment placed on this face in the z direction is leading to this integral of E over rho times y squared across the surface. So what we've determined is that the net torque that's put on this surface by the adjacent surfaces is equal to EI over rho. But the net torque that's put on this surface from adjacent surfaces is exactly the internal bending moment that's applied to this surface. So that is why the internal bending moment has to be equal to EI over rho. It tells you how curvature is going to be manifesting in this beam in response to the internal bending moments just by looking at the net effect of stresses and how they're related to strains. And that determines for us this Hooke's law relation that applied moment is going to lead to a curvature through flexural rigidity. Okay, so we're going to do an example that involves figuring out flexural rigidity and all the bending stuff of a particular beam. Let's put some numbers to this, or at least variables to this. Suppose we have a Young's modulus E, a uniform one. It's a rectangular beam, and it goes from 0, 0, 0 to LHB, and we're going to put a moment on it in the width direction, in the Z direction. So moments in the Z direction, if it's a positive moment, that's going to cause it to bend up like this, into kind of like a smile for this beam like that, right? So we're going to look at this surface, the length direction here, this surface, and figure out the resistance to moments applied to that surface in the Z direction. All right, there's some analytical work below on this, but let's just do it in Maple up here. So we've got that the cross-sectional area, AX, area perpendicular to the X face, would be equal to the, not the length, but the thickness times the width, right? Thickness there and the width, okay? And this is, maybe we can write down what those things are. We might call it like LX, LY, LZ. I guess that's a little bit easier to remember, but we've got it here in the picture. So X is the L, the length in X is L, length in Y is H, and the length in Z is B. Okay, so there's the cross-sectional area. It's the length in Z, B, times the length in Y, H. The location of the stiffness-weighted centroid of this surface would be Y bar is equal to the integral. We're going to integrate over this whole surface, integrate the with respect to area, so there'll be two integrals, of what? The y coordinate times E. Now E is just a constant. E is equal to, well, I guess just E, right? We're not going to put in a number, but E doesn't depend on y, right? In this, sometimes it can. Sometimes you can have an E that is different at the top versus at the bottom, and then we'll have a y bar that's not just in the middle, but here, with no dependence on it, we should get something that is just right in the middle. So we'll go y equals 0 to H, and then the Z is going to be integrated from 0 to B. And we're going to divide this by just the integral of not y, but the integral of 1 times e. It's a weighted average integral. So the e is not going to matter. It cancels out of the numerator and denominator, and we should end up with y by the maximum y, which is h, divided by 2. Aha, got it. Similarly, we can figure out z bar. How would we do things differently? Z bar, well, first of all, it should just be in the middle again because there's no there's no z dependence in the stiffness. But how we would do it in brute force method is we'd have the same weighted average, but it's not a weighted average of y anymore. It's a weighted average of z. So the thing that we're averaging, we would replace the function, which is just in this spot, has nothing to do with the rest of it. That's just taking us as an integral over that whole area, over the y range and z range for this rectangular region. All we need to replace is this thing from a y with a z, and we're going to have the average z value now, which is b over 2. So we start at z equals 0 here, go all the way to z equals b. So the average z, weighted by stiffness, which doesn't depend on z, is just b over 2. All right, next is second moment of area of its YZ cross-section about the Z parallel axis through the centroid. So the axis parallel to Z that goes through the beam's centroid. That's important because that's going to be the one that is for bending for this thing. So we can call that, let's see, I, maybe ZZ, moment for bending about Z, you'll sometimes see that. And this is... or maybe IZ about, what would we call it, like Y bar or something, for bending about that centroid location. That will be a similar integral to this, right? Except that you don't divide by the integral of nothing. So where am I getting this from? This is from the definition of I up here, which is the integral over the area of the position minus y bar all squared. Okay, so we're going to substitute that in. We've got not an e anymore. We've got the position minus y bar all squared. And now we're integrating that over the area. So this should tell us what iz of y bar is. Okay, and we've got that it is h cubed times b divided by 12. If that looks familiar, then you might be remembering the moment of inertia of some uniform density rod about the center of it is 1/12 of the mass times the length squared. So the length in the whole dimension squared. If you were to take out mass and just put in density times the volume of this thing, then you would have another width and the thickness and then length cubed. So that area stuff, length cubed over 12, is the same stuff that was showing up in moment of inertia. Now, so the reason for that is this is a representation of how difficult it is to rotate something around a center, and that's the same kind of thing that's being dealt with here. So here, this is just from an area perspective. How hard is it to rotate this cross-section? How much does a cross-section resist rotation about its central axis, and ends up being an integral of the square of the distance away from that axis, which is what's leading us to this h cubed b over 12. So the width matters, but the thickness matters 3 times as much. So it gets 3 factors in this multiplication compared to the width's only 1 factor. So after that, we're going to figure out the flexural rigidity. And we could figure out the flexural rigidity by taking iz y bar times e. And that's fine for this situation. It'll just be the second moment of area we calculated about the neutral axis multiplied by e. But more generally, we should find the flexural rigidity most of the time later. To be more general, we're just going to skip this step because this is not what's quite important. As you saw from the derivation above, you really need to leave the e and the square of the distance from the neutral axis and even the radius of curvature in that same integral where this derivation came from to be able to get things correct. So what we want to do is just directly take e multiplied by the square of the distance from the neutral axis, and then integrate that over the area to find flexural rigidity. Again, it's not going to make a difference if E doesn't actually depend on position, but this one is more general, which is going to still calculate the flexural rigidity if you have something like a steel and a wood beam bonded together, and the cross-section has a different stiffness at different Y values. So what units do we have, by the way? We've got that the second moment of area is meters to the fourth, whereas the flexural rigidity is meters to the fourth times pascals, which is newtons per meter squared. So overall, it ends up being Newton meters squared as the units for flexural rigidity. To find the curvature, we're going to make use of the formula that the moment is equal to EI times the curvature. So then the curvature is just equal to the moment in Z that we're applying divided by EI. And that's it. So you can see that the curvature is going to be linearly proportional to the moment, inversely proportional to the stiffness of the beam in the length direction, inversely proportional to the width, and inversely proportional to the cube of the thickness. And there's that paper thing coming into play. The paper being much, much thinner leads to much easier curvature happening. Here's an example of me doing this with a piece of single crystal quartz that's been coated with some molybdenum here during the PhD work that I did at McMaster. And you've got this little membrane of quartz, which is about 7 microns thick. And because it's that thick, even though it's single crystal quartz, which is a very brittle substance, it is able to curl and uncurl no problem. So it curls up from the difference in strain that's been put on each side of it and is able to flatten out and go back, no issue. You cannot take a pane of glass and roll it up like this, like you can with this quartz. And the main reason why is this quartz is so thin. So again, the thickness is what's responsible for the majority of resistance to bending through this factor of h cubed there in the denominator. So curvature is related to radius of curvature by them being inverses. Once you've got this, you can say that rho is equal to 1 over c. Bending angle is related to the length and the curvature. So bending angle is going to be L divided by rho, or phi is equal to L times c multiplied by the curvature. And this kind of makes sense too. The longer it is and the more curvature you have, the more of an angle it's going to bend through. Let's have a look at those things. The radius of curvature, not surprisingly, just 1 over c is the inverse of this previous formula. And then the angle, because it's just the curvature times length, has brought in length into that. So the actual bending angle you get is product of this curvature thing multiplied by the length. Do the units make sense? Yes, so angle should be unitless if it's going to return something in radians there. And we've got curvature having units of inverse length. Let's check. We had that EI was Newton meters squared. And curvature is moment, which is Newton meters divided by Newton meters squared. So it's inverse meters, which is why rho, 1 over c, is going to be in units of meters. And phi, which is 1 over meters times the length in meters, is going to be unitless. Next up, let's look for the maximum tensile compressive stress. Okay, this is going to rely on going back to this proof that we had earlier, where we said that the stress was the stiffness times the displacement from the neutral axis divided by rho, or displacement times c. So this tells us that the maximum stress, whether it's tensile or compressive, depends on whether moment is positive or negative. Let's assume that mz is actually positive. Then the maximum compressive stress is going to be at the top, and the maximum tensile one will be at the bottom. So we can say sigma max tensile is equal to the, looking at this, the stiffness, E, times 1 over the radius, which is times C, multiplied by the largest we could make negative y. And the largest we could make negative y is when we put in y is equal to negative So this y was relative to the neutral axis. So it's when we put in the farthest away we could be below that, negative h over 2 in this problem. That's the farthest away from the neutral axis. So negative h over 2 will be just h over 2, and that's the maximum tensile stress we can have. Okay, so the maximum tensile stress is this moment divided by h squared times b. And this shows you something else. The stress that is showing up in something is, yes, proportional to the moment, but it's inversely proportional to the square of the thickness of this thing. As an example, let's see what the maximum stress is to cause something to bend to a 90-degree angle. So we're going to put in as much moment as is necessary for a thing to bend to 90 degrees. And that gives us an ability to solve for the moment. So let's say solve phi equals pi by 2 for the moment. And this tells you what the moment has to be. And let's say that the moment is equal to that amount. Now we've got a fixed moment as whatever moment is necessary to make the thing bend to 90 degrees. And that tells you that the maximum stress that you're going to get it to bend to 90 degrees is the Young's modulus. So higher Young's modulus is going to need more stress. Pi by 4, so just a geometry value there. And then the thickness divided by the length. So the longer the length, the less stress it's going to take for this to bend to 90 degrees. That kind of makes sense because the same stress, the same moment, will cause this to bend more of an angle if the thing is just longer, right? And it's proportional to the thickness. So if you have, let's just kind of estimate what was going on for that quartz there, right? For the quartz membrane that we have H is equal to about 6 E minus 6 microns. We have a stiffness. Let's just leave stiffness as regular for now. We have a length, which is roughly 8 millimeters. And let's see how much tensile stress we need to do that. So the maximum tensile stress to get a 6 micron thick, 8 millimeter long membrane to curl 90 degrees is 0.06% of the Young's modulus. And that means that the strain that it will be in is 0.06. And 0.06 is the kind of strain where for the right material, like single crystal materials, you can have not enough stress for it to actually break. So that's kind of amazing. If you had a thicker thing, like let's imagine instead of 6 microns, it is 600 microns, then we're going to end up with a maximum tensile stress showing up, which is 6% of the Young's modulus. Rather than 0.06%, we have 6%. So this is not surprising because we found that the stress, before we put in these numbers, is proportional to the thickness. So if you take the thickness up by a factor of 100, then you have 100 times as much stress max at the edge. And that means that you're going to need a material that can survive 100 times as much strain for it to be able to deal with that kind of bending. So the easiest way to get a material to bend a lot and be able to still survive is to make sure that the length to thickness ratio is very high. This thing is an I-beam. It's called an I-beam. Why do you think that is? Well, because the cross-section is in the shape of a capital letter I. It is much more difficult to machine than just like a straight bar there, like a rectangular thing. If you were to smush this all together, the same amount of steel into a pure rectangular cross-section, but this is much more common to see in building construction. Why do you think that is? Because this calculation of the second moment of area cares about the square of the distance away that a little piece is from the bending axis. So this is designed to maximize the amount of area at a faraway point from the bending axis. This beam does way more resistance to bending than if the same area were just in a rectangle, right? So this is used because it is going to have a large amount of area far away from the center. Let's compare the flexion things to what we had before for Hooke's law and stress and strain. In axial loading, we had that the stress is the perpendicular force per cross-sectional area, and this leads to a strain, which is in the normal direction and related to the slope of the normal displacement per step in that direction. And the Hooke's law that relates the strain and the stress is that the stress is equal to the stiffness times the strain, where you'd have to use effective stiffness in the length direction, but still just the resistance to stress in the length direction is the Young's modulus. For shear, same kind of idea. The shear stress is the parallel force per area, and this led to a shear strain, which is the sum of these partial derivatives of displacements. And the shear stress is related to shear strain through the shear modulus. For flexure, you could say that the equivalent stress is like the moment divided by the second moment of area, and the strain, we're looking at the curvature, which turns out to be the second derivative of the transverse displacement with respect to step in the length direction. And so we can prove this by looking at a circle, a circular section very closely, and seeing that for a small step in the x direction, the transverse displacement second derivative is equal to this curvature that we're finding. We'll have a look at that later. And the Hooke's law that relates this stress to this strain is actually just that this thing is related to the curvature through the stiffness, the same one as for axial stress and strain. And that's because bending is the result of lots of contributions of just axial stiffness of this material in response to stresses on the local level. All right, what about flexural rigidity for multi-layer beams? A lot of the time you end up with a beam that isn't just one material uniformly across the cross-section, but multiple materials. So maybe it's like some gold and then some molybdenum, and then you've got some tungsten up there, and then there's some more molybdenum there. Okay, kind of a cool beam. If this has multiple layers with different parameters, then the average density and Young's modulus end up being weighted averages across the cross-section. So if you have discrete layers, then you could use sums. Otherwise, you'd have to integrate in general. The average density would be, from the average we defined above, integral of density over the cross-section divided by the total cross-sectional area. Same thing for stiffness. In response to the motion in the length direction, in response to stresses in the length direction, the effective stiffness in the length direction of each layer averaged over the cross-sectional area will give you the average stiffness. Now you could use just these discrete sums unless you really had continually varying parameters. You can always use the integrals if you want to set up like a piecewise function for the density and the stiffness, and then just deal with these definitions anyway. And with Maple, that's actually probably easier. But these are necessary to use if you have continually varying parameters. You can get that, as a fun fact, in the 3.5 semiconductor molecular beam epitaxy machine, or the chemical vapor deposition machines in the tandem accelerator building here at McMaster. These can continually grow single crystal materials that have continually varying parameters. So if you want to say that it starts off with gallium arsenide at the bottom layer, and then it gradually turns to indium gallium phosphide by the time you get to the top layer, you can do something like that. I'd have to look up those exact parameters and see if it would survive over the length that you're going for. But in principle, you can have continually varying parameters grown in those machines. So you might have to use integral methods to figure out the effective density and effective stiffness in the length direction. For flexural rigidity, you can also dive into a sum type version that involves you figuring out what the flexural rigidity and EI weighted centroid of each layer is, the stiffness weighted centroid of each layer is, and then have a sum that adds them all up and compares one axis's second moment of area about its center to what happens when you displace it using the parallel axis theorem. But rather than doing that, you can just work with the location-dependent parameters and integral methods right from the start. So these equations that we worked out up at the beginning are also going to work just fine if you have stiffness that depends on location. So you don't need to worry about this sum version if you have a computer algebra system and can just put in the stiffness that depends on location using piecewise functions. Okay, let's check out the next example using this. We've got a bimetallic strip that's 30 centimeters long and is 3 centimeters wide and 1 millimeter thick, shown here, not to scale, and it's made of 2 layers. We've got a tungsten layer that's on the bottom, and the tungsten layer is thin. It's 30% of the thickness, and an aluminum layer, which is on the top and is 70% of the thickness. And we've got the material parameters for tungsten and for aluminum. And they ask you to calculate the linear density, mass, combined axial Young's modulus, flexural rigidity, and flexural rigidity of the strip. And let's see. Then what do we have? We have another question here. Well, this is sort of strange. It's like there's 2 questions in one. So let's say that this stuff was actually just forgotten, and we've got the question down below. Calculate the linear mass density, combined axial Young's modulus, curvature, radius of curvature, and arc angle that results from a bending moment of 1 Newton meter applied in a way to make it bend. So what kind of bending are we going to have? Let's say that this is applied in the Z direction. Maybe we'll say maximum arc angle. Maximum arc angle that results from a bending moment of this. And that tells you that the bending moment has to be applied in Z in order to get this arc angle to show up. So next we have to incorporate this into Maple. I'm going to put this on a couple of different lines so we can see it all at once. The aluminum is that % of the thickness. Calculate the linear mass density, combined axial Young's modulus, curvature, radius of curvature, and maximum arc angle that results from a bending moment of that. Okay, cool. Now let's get started with this. So we could use some of the same formulas as before, but some things are going to be a little bit different. So maybe let's just give a shot again and see what we remember of the previous stuff. Okay, so the length is 30, the width is 3 centimeters, and the thickness is 1 millimeter. And we've got 2 different layers. So we can, it's up to us where we want to say that the transition is between the layer, where the neutral axis is. We can put the neutral axis at the bottom, or we can put, or wait a minute, not the neutral axis. I mean the y equals 0 position. We can put that at the bottom, or we can put it at the junction between the two. Maybe let's put it at the bottom. So let's suppose that y equals 0 is defined as the bottom, and then we'll say that E is equal to piecewise if y is less than 0.3 times h, because that's going to be the location of the junction between the two, right? The tungsten, the aluminum layer, which is on top, is 70% of the thickness, so that means the tungsten is 30% of the thickness. Maybe we'll call this yj for the junction. Yeah, let's do that. Yj is equal to 0.3 times h. All right, so if y is less than yj, then we've got the Young's modulus of the tungsten, 411E9. Otherwise, we've got 70E9, aluminum's Young's modulus. Now, what about the density? Well, let's do Poisson's ratio next. Nu is equal to same setup, but Poisson's ratio of tungsten, 0.28, and then Poisson's ratio of aluminum on the top, 0.35. And then we're going to have the density. Rho is now just the density, so we better not use that for radius of curvature later. Better just use C for the curvature. So anyway, density, tungsten should be a lot more, is 1925. Now this is grams per cubic centimeter. So in order to go to kilograms per cubic meter, we're going to be dividing by 1,000 to go from grams to kilogram, and we're going to be multiplying by 100 cubed, which is 1,000,000, to go from per centimeter cubed to per meter cubed. So divide by 1,000, multiply by 1,000,000, we'll be multiplying by 1,000. And that means it's 19,250 kilograms per cubic meter. Just as a check, if we had water, the density would be 1 gram per cubic centimeter, and the mass of a cubic meter of water is 1,000 kilograms. So that means we're on the right track. We multiply this by 1,000, a density of 19.25 grams per cubic centimeter means that a cubic meter of this thing would be 19,250 kilograms. Right, quite a heavy cube there. That's a lot of tungsten. Next, aluminum, we've got a much lower density. Still, I wouldn't want to be under a cubic meter of aluminum because that is quite a lot more kilograms than I am. So I think the aluminum would be in better shape than me there. Next up, the calculations. Linear mass density means the mass per unit length, and that's going to be the integral of the density, which is mass per unit volume, over the cross-sectional area. So we can figure that out. Let's see. We are going to say mu, the mass density, is equal to the integral of the density with respect to volume. So we need to integrate across z. Z is equal to Z is going to range from 0 to B, and Y is going to range from 0 to H. So that's one way to set this up. Since none of the parameters depend on the Z value, we could, instead of doing this, set up an integral that just multiplies by the width and then only integrates with respect to Y. That's fine too. This is also like integrating with respect to area, keeping in mind that we don't have any dependence on Z. So whatever way you like, this one's fine too. This is maybe a little bit more convenient for incorporating a width that depends on the Y value too. So if you have this beam that is a different width at the top versus a different Y value, then writing the area integral like this will be a little bit more convenient for incorporating that. So either way, whatever way you like. So this is the combined, this is the total linear mass density. It looks a lot lower than the other density. It says if we had a meter of this, then the thing would only be 1 times this density kilograms. So it would be 0.23 kilograms if we had a meter long of this thing. Why is that? Well, because it's so small in the cross section. It's not a meter by a meter in the cross section like the cubic meter of this would be. It's only 3 centimeters by 1 millimeter. Quite a lot smaller than the cubic meter here. So the combined Young's modulus is going to be calculated by taking a weighted average, well, actually just an average, of the average of the Young's modulus across the cross-section. So we'll take the same integral, but instead of integrating the density, we'll integrate E, and then we'll divide by that integral just by itself. So this is dividing by the area. And you'd expect that the Young's modulus we get is going to be somewhere between tungsten and aluminum, but closer, tungsten and aluminum over here, closer to aluminum's because aluminum is 70% of the thickness and tungsten is only 30%. So let's check. We've got 172 E9, so 172 gigapascals, which is indeed a little bit closer to, actually a lot closer, I guess, to the aluminums than to the tungsten. How far away are we from the tungsten? That's about 230 away from tungsten, and it's only about 100 away from the aluminum, so more than twice as far from the tungsten one as from the aluminum, because the aluminum is more than twice the thickness that the tungsten is here. Next up, we're going to figure out the curvature, and this is curvature, radius of curvature, and maximum arc angle is going to be a fair bit of calculation. And what do we need for this? Well, we need the moment that's applied. The moment is going to produce the most curvature if it is in the direction that leads to the most bending, which is the one whose bending resistance is the weakest, and that's going to be in the thickness direction. Remember, thickness is very important, so if we have a 1 millimeter thickness as opposed to a 3 centimeter thickness, it's going to be much easier to bend in that 1 millimeter thickness direction. So let's figure that out. We said that the curvature is equal to the moment in Z divided by EI. And then we're going to be able to get the radius of curvature by saying ROC, radius of curvature, because we already used rho for something different, is 1 over the C. 1 over C. There we go. And then the maximum arc angle, phi, is equal to the length times the curvature. So that'll be all good. All we need to do is put in what those parameters are, figure out what the moment in Z is, and that we're given. Mz is equal to 1. Then figure out what the flexural rigidity is, and we'll have it. Okay, so what is the flexural rigidity? Well, EI is equal to the integral over the cross-section, so we'll have integral of B times E times the square of the distance from the stiffness weighted centroid of this thing. Not divided by anything else. So EI is not an average, it's just the integral over the cross-sectional area, so that's why we've got the integral over all the y values, and nothing depends on the position in Z, so we're just multiplying by B rather than doing that integral explicitly with respect to Z, of E times y minus y bar all squared. Now to do this, we're going to need to figure out what y bar is. So y bar is equal to the integral. It's actually kind of similar to this thing. It's the integral of B times E times Y from Y is 0 to H over the integral of B times E from Y is 0 to H. So what is this? It's an average Y position where we are weighting that average by the stiffness. So this, first of all, predictions. We don't expect this to be exactly at the halfway point this time. It's not going to be at 0.5 millimeters. It's going to be closer to the tungsten because the tungsten is so much stiffer than the aluminum that once we're weighting this weighted average by the stiffness, we're going to have something that is a lot closer to the location of the tungsten. So probably closer to 0.3 millimeters and maybe even within the tungsten itself. Let's see. It is, yeah, just slightly within the tungsten. So 0.29 millimeters up from the bottom of this beam inside the tungsten itself because the tungsten is so much stiffer than the aluminum. All right, now that we've got that figured out, we can figure out EI, and there we go. And then we'll get the curvature, the radius of curvature, and the angle. So the next thing has us actually take advantage of this ability to deal with different widths and say, suppose that the bottom is only 1 centimeter wide instead of 3 centimeters wide. How could we deal with this? Well, we'll say that the width, B, is actually not always 0.3, but depends on what the height is, what position we're at, what spot we're at. So if we're below yj, then we'll say that the width is only 0.01, but if we are greater than yj, then the width is 0.03. So this, let's just check with everywhere that we were using the width, is this going to account for things correctly? So now this first integral will be taking it from 0 to b, and it actually should still perhaps be dealing with things correctly by taking the end range of this at the value that is now dependent on what the y parameter is. By doing the y integral next, I think we've actually accounted for it in this first one, and both the mu's should still be the same. Yeah, then we've got the integral of b over the thing, so that should be good. All right, let's just check. Right, so same linear mass density calculation either way, whether we just say that the integral of rho from z is 0 to b is going to be rho times b, or we let the integral go and calculate itself with B, again, depending on what the Y value is. And then incorporating the rest of these things. First of all, what's the prediction that we think about this? If the tungsten is less thick or less wide, then the average Y position should move up. It shouldn't be this 0.292. Yeah, it's 0.42 millimeters, much closer to the center of this beam, much closer to the center of the aluminum, because the tungsten, although it's a lot stiffer, is a lot less, has less area now. The product of the stiffness and the width is what matters for this resistance here when we're figuring out the average, the average Y position weighted by the stiffness. So by making the tungsten a lot thinner, it's kind of counteracting the fact that it's a lot stiffer and leading us to a Y value that is closer to the middle of the aluminum. In the extreme, if we were to take the width to not 0.1 but 0.01, then we should end up with a Y bar, which is a lot closer to the middle of the aluminum. Yeah, so the aluminum goes from 0.3 to 1, and the middle of that would be what, 0.65, right? Yeah, so we're getting a lot closer to that. If we take it to 0.001, then we're getting very close to Y bar just being right in the middle of the aluminum. Right, okay. So this gives us, how does the angle compare to before? If we make the tungsten less thick, then we should be getting more angle than we had last time, where it was 0.85. Yep. So the same moment is going to give us a lot more bending because we have less resistance, a lot lower flexural rigidity than we had earlier.